So as we jump into our Module 9 here, we're finishing up our chapter on transient conduction right here. And again, in particular, looking at our spatial effects and the role of analytical solutions in our Module 9.1. And in Module 9.2, we'll look at our finite difference equations. So within this whole module here, we're going to look at situations frequently where the Biot number is not small. So that right there means that we're going to have to deal with the fact that temperature gradients within a medium are no longer negligible. So we can't make this assumption anymore. So the use of lump capacitance method would yield incorrect results. So everything we looked at before in the previous modules there using lump capacitance won't work for this situation here. So we're going to need to take a look at some alternative approaches that we can use. We're also going to take a look at implicit and explicit forms of our finite difference solutions to transient conduction problems as we get into Module 9.2. So objectives within this module, we're going to take a look at our spatial effects, talk about the plane wall with convection, look at the radial system with convection, talk about the semi-infinite solid, get into some objects with constant surface temperatures or surface heat flux, and then last we'll get into this finite difference method. So as this relates back to our textbook here, these are our reading guides down here as we wrap up Chapter 5. For Module 9.1, we're taking a look at transient conduction, dealing with our spatial effects and the role of analytical solutions, in particular looking at some alternative approaches. So within this here, some of the objectives we'll be looking at here is our plane wall with symmetric convection conditions. We're looking at our Heisler charts, some radial systems, going over some semi-infinite solids approaches, and dealing with objects with constant surface temperatures or surface heat fluxes. So within this here, we'll go through the governing theories, take a look at some key equations, talk about some practical applications, and then go through some problem solving together. So for this Module 9.1, we're going back to Chapter 5 in our textbook here, sections 5.4 through 5.8. Again, we're looking at our transient conduction, the spatial effects, and the role of analytical solutions. So a couple things that we want to mention right here. Situations frequently arise where our Biot number is not going to be small. So that was an assumption we made in previous calculations right there. So if this is not small, we must cope with the fact that these temperature gradients within the medium are no longer negligible. So again, another assumption we made that these were negligible. That's no longer the case for these small Biot, or these larger Biot numbers right there. So the use of this lump capacitance that we went through in the previous modules would yield incorrect results. So if that's not going to work for us using that method right there, we're going to have to take a look at some alternative approaches. So that's what we're going to be taking a look at within this Module 9.1. So continuing on with this, let's take a look at a simple situation here where we have a plane wall with symmetrical convection conditions right here. So if we want to find the solution to the heat equation for this plane wall right here, what we would realize is for a small Biot number, the lump capacitance method no longer is possible. So if this lump capacitance approximation cannot be made because it has a larger Biot number right now, then a consideration must be given to our spatial as well as our temporal variations in temperature during the transient process. So now let's take a look over here at our plane wall in this figure right here, and we can see, okay, there's our center line right here. We can see we go out an equal distance to L right here in our x direction here, and a distance of L right here in our negative x direction there. We can see we have a initial condition right here, that we have our T at a position right here of x right here is equal to T sub I, our initial temperature right there, and we can see we have our surrounding T infinity and H values symmetric on either side of this wall right here. So this is for a plane wall with symmetrical convection conditions and constant properties that we've just shown in our diagram off here to the right. So the heat equation and initial boundary conditions are given as the following, and this relates back to equations 5.29 to 5.33 in your textbook right there, where 5.29 gives us our initial temperature distribution plane with no internal generation and the assumption of constant thermal conductivity right there. So that comes down to this 5.29 there. We have our delta squared T over dx squared right there. So it allows up to x right there. This is equal to 1 over our alpha times our dt right there, our delta of temperature right there with respect to time there. So that's our equation 5.29. So then we can take a look at our initial condition here in equation 5.30. So this initial condition presumes a uniform temperature at time t is equal to 0. So you can see right there, there's our t is equal to 0 for any x right there. So temperature for any x at time is equal to 0 is equal to our initial temperature right there, T sub I. So this is a uniform temperature distribution regardless of where it is, where the location in x direction at initial time of T is equal to 0. Then we can go on to our boundary conditions, and in equation 5.31 we look at the boundary condition here that reflects the symmetry requirement for the midpoint plane of the wall right there. So again, we saw that there was symmetry about that right there. So with this here, we have our partial of t with respect to x, partial of temperature with respect to our position in the x direction going out like this here. When x is equal to 0, and we're right at that midline right there, then our partial of temperature with respect to x is also equal to 0. So again, that goes back to a relationship shown here in equation 5.31. And our next boundary condition here, equation 5.32, this describes a surface condition experienced for a time greater than 0 right there. So when it's not a time of 0, when it's greater than 0 right there, we can say our negative K, our thermal conductivity right here, times our partial of temperature with respect to position, delta T, delta X, right there, evaluated at some X is equal to L. So L is out here at the end right here, at the outside walls of this right there. This is equal to H. There's our H value right there, the same on both sides right there for convection right there, times now our temperature difference between now our temperature of L comma T. So when X is equal to L and our time is equal to some T right there, which is a time greater than 0 right there, minus temperature of our surrounding, T infinity right there, and this is now our equation 5.32. So with this here, we can go on to equation 5.33, and this shows the existence of 8 independent variables right here. So we can take a look. T is equal to T of our X, position X right there. So coming off of this is our X right there. Our time, initial temperature, temperature of the surrounding, our value of L right there out the outside surface, our thermal conductivity, our alpha term, and our H term as well. So all these are 8 independent variables that are shown right here that our temperature is dependent upon right there in equation 5.33 in our textbook. So now I want to talk about the non-dimensionalization of the heat equation and initial boundary conditions. We're going to do this still for that plane wall example we saw on the previous slide right there. So within this here, let's first take a look at our dimensionless temperature difference right here. So we have our theta star right there. So our star right here is going to denote this is dealing with dimensionless right there. So this is equal to our theta over theta I right there, our temperature difference over our initial temperature difference right there, which relates to equation 5.34 in our textbook right there, where we have our T, our temperature of interest right there, minus our T surrounding right there, T infinity, all over our initial temperature minus the temperature of the surrounding right there. So that'll give us our dimensionless temperature difference right there. So next, let's take a look at our dimensionless space coordinates. So recall here, if we're dealing with space here, we're dealing with our X direction here for this 1D plane wall. So this is going to be our X star right there, which relates back to our equation 5.35 in our textbook right here, where we have our X over L, where our L in this case here, if you remember back to that diagram of our plane wall right there, L is going to be half the thickness of the plane wall because it's going to be symmetric about that midline right there. So from there, if we're talking about our dimensionless space, let's also talk about our dimensionless time right here, or our T star right there. Now this is going to be equal to our alpha over L squared right there, which is equal to our Fourier number. So we call here our F sub 0 or F sub O right there is our Fourier number there. So that's saying our dimensionless time is our Fourier number, and this is our given relationship right there, this alpha T over L squared right there. And this relates back to equation 5.36 in our textbook. Now from here we can go on to our Biot number that's dimensionless as well. Recall that this relationship here is our Biot number is equal to our H times our L right there, all over our thermal conductivity K value for the solid right there. So this, recall, is our Biot number that we've seen previously. So with all this here, now what we can say is that this theta star right there, our dimensionless temperature difference right there, is going to be a function of our X star, which is our dimensionless space coordinate, our Fourier's number, which is also, as we just saw up here, our dimensionless time unit right there, and our Biot number. So all of these are dimensionless right there. Our X star, our Fourier number, and our Biot number right there. So this is what our theta star right there, our dimensionless temperature difference, is a function of all three of those. So now if we want to take a look at our exact solution, we have some equations that we can reference back in our textbook. Particularly, let's take a look at this equation 5.42a, where here now we have a relationship for our plane wall right here for our theta star right there, which again is our dimensionless temperature difference right here. And this is equal to the summation from n is equal to 1 to infinity right here of our Cn times the exponent here of a negative eigenvalue squared times our Fourier number right here times the cosine of our eigenvalue times our X star right there, where again we come back up here on our X star is this dimensionless space coordinate right here, where again this we're still dealing with our plane wall right here, and L is the half thickness of that plane wall right there as we plug in for that X star right there for our dimensionless space coordinate. So that makes up our equation 5.42a. Now the question is, well, what is this C sub n right here? Well, we have this relationship here that our C sub n is equal to 4 times the sine of our eigenvalue, all divided by 2 times the eigenvalue plus sine of 2 times our eigenvalue right there. And we also have the relationship now in equation 5.42 here for our biot number. So our C sub n and our biot number, we can reference back to 5.42 B and C in our textbook right there, where our biot number is now our eigenvalue times the tangent of our eigenvalue there. Where now the question is, well, what are these eigenvalues right here? So we can go to our appendix B3 in our textbook. And we can look at the first four roots for our eigenvalues for 1, 2, 3, and 4 right there and plug it back in to this equation. So now let's actually go to the appendix in the back of our book, take a look and find our appendix B3. So again, in B3, this gives us the first four roots of our transcendental equation right there. So we can look up our values, our eigenvalues right there, and recall right there we have that relationship we just saw in our previous slide. It even gives it to us in that appendix right there, that our eigenvalue times the tangent of our eigenvalue is equal to our biot number. And this is for the transient conduction in a plane wall. So again, we're just looking at transient conduction for that plane wall example from before. We also see now there's our relationship for our biot number right here, where biot number is equal to h times L over k right there. So now we can look here for our eigenvalues again, the first four roots, 1, 2, 3, and 4, all given in this table right here for these biot numbers right there. So next I want to take a look at some approximate solutions. In particular, let's take a look at our one-term approximation. What we want to note about this one-term approximation here is this is only going to be valid for Fourier's number greater than 0.2. So in order to use this approximation right here, we need to make sure that this is valid right here and that Fourier's is greater than 0.2. We see that the variation in our midplane temperature right here, and again, we go over here, what is our midplane right there? This is our midplane right there. So this is when x star is equal to 0 right there, going right up that there. So you can see that's our x value going over here. So when this is equal to 0, we're at that midplane right there. And with a time of our dimensionless time, our Fourier number right there. Again, we go back to our previous slide, and we can see that this Fourier number is our dimensionless time. So for that, then we can say that this equation 5.44 holds true right here, or we can say our dimensionless temperature difference, our theta at that midplane right there, star is equal to our temperature at the midplane minus our surrounding temperature right there, all divided by our initial temperature minus our surrounding temperature there, which is equal to our C1 times the exponent of our eigenvalue squared times our Fourier number right there. So again, this references back to equation 5.44 in our textbook. Now for our values, our coefficients right here, our C1 and our eigenvalue one term right here, we can go to our table 5.1 in our textbook and we can get these, and we can see that these two coefficients are a function of our biot number. Now we can also evaluate these coefficients with equations 5.42b and 5.42c in our textbook. So looking at the variation of temperature with our location, our dimensionless location right here, our x star, and time right here, Fourier's number, our dimensionless time right there, we can go now to reference equation 5.43b in our textbook that tells us that our theta star right here, our dimensionless temperature difference, is equal to our theta 0 star, this is our at the midplane right there, which we have this equation up here from 5.44 for that right there, times the cosine now of our eigenvalue times our x star right there, which is our dimensionless space coordinate right there. So this references back to equation 5.43b in our textbook. Now moving on from there, if we want to take a look at our change in thermal energy storage with time, we have these equations here, 5.46a, 5.49 and 5.47 in our textbook right here, or 5.46a shows us this delta E right here, our change in our thermal energy storage is equal to our negative Q. Well, the question is, well, what is Q? That's where we can go to equation 5.49 in our textbook and see that Q is equal to our Q not right there, Q at 0 right there at our midplane right there, times 1 minus the sign of our eigenvalue 1 all over our eigenvalue 1 there, times now this relationship right here for our dimensionless temperature difference, which we see we have this equation for up here in 5.44. And then we can say, well, what is our Q at 0 right there? Well, Q at 0 is 0, which is our midplane right there, is equal to rho VC times our temperature difference, our initial temperature minus our surrounding temperature right there. So we need to plug all these in. We can plug this relationship in for our Q naught right there, and then we can multiply that by this relationship right here, and that whole term right here comes up here with a negative sign in front of it right there, and that gives us our change in our thermal energy storage with time. Now let's go back and take a look at our textbook here at the table that we referenced there, our table 5.1, where this gives us the coefficients used in one-term approximations. So again, this is just for the one-term approximation to the series solutions for transient one-dimensional conduction. So very specific right there. Make sure when you're using these tables, you do look at them and see what they apply to. So that's the case here. We can see now we have our Biot number right here, and we can see our eigenvalue and our coefficients right here for a plane wall, an infinite cylinder, and a sphere. So we have for all three of those simple geometric shapes. So as we're talking about approximate solutions, we can talk about looking at some of our charts. In particular here, our Heisler charts here. So if we want a graphical representation that we can get an approximate solution from, in this case here for a one-term approximate solution right here, we can look for our mid-plane temperatures for these charts right here and reference back. And again, this is going to be an approximation because we need to come down here on our x-axis, go up to whatever chart we're using right here. So you can see these are our inverse Biot numbers on this chart right here, which is our K over our HL right there. We can come down here on the bottom. There's our dimensionless time right here, our Fourier's number on the bottom right there. So we go up from that there, then we can go up from one to the other, see where it intersects, then come back across over here and get our dimensionless temperature right here, our theta star right there. So we can utilize these charts, but again, this is a very small condensed chart, and this is only going to be an approximate solution when we utilize these charts to do that. But they are a good double check, a good reference if you've done this out by hand and the other methods that we saw above there and actually did out our calculations. We want to double check and make sure that it is similar to what we're seeing on these charts. This is a great double check as a reference as well to use these Heisler charts. Now we also have these same charts here for our temperature distribution and our change in thermal energy storage right there. So again, we look at here, we have our inverse of our Biot number right there. The bottom we come up here and there's our value for our x over L for each of these curves. So again, we can do the same thing. Let's just say we were at, let's say here a value of 0.2 right there, and we go up to this value right here for 1 for the h over, or x over L right there. Then we can come over across here and we can get our value here for our theta over theta naught right there. Theta sub 0 right there for our temperature distribution right there, which again we recall is this relationship of temperatures right there between those differences. And then if we come down here to our change in thermal energy storage right here, similar, we can take a look at our x-axis down here for our Biot square times our Fourier number right there. Come up here to our Biot number as one of these curves on the chart right there. Then we have our Q ratio over here, so we can do the same thing, come up till we hit the curve that we're interested in, then come back across to get this value here. So again, as you can see, this is going to be approximate solutions. I would highly recommend getting a ruler if you're going to use this and get as accurate as you possibly can. Again, you see this is a very fine scale, very fine logarithmic scale in that case right there, where you're going to need to come up and really pay attention to how close you are, and then draw a line straight across perpendicular to that to come over here to your y-axis to get your values. But again, this is a great double check. Once you've done this out, you can see you have the equations here. You can do these equations out and get your values that way and then double check them on the charts, and that's how I would suggest doing that. Other problems, you may need to use these charts to get values. They may not give you enough values, and you can come to these charts in order to back out a value you need to solve one of the problems. So another case, and you've seen this all in your thermodynamics courses previously, utilizing charts similar to this. So now instead of a plane wall, let's take a look at a radial system here. So for a radial system, we could be dealing with a long rod or a sphere that's heated or cooled by convection for this situation here. So we can see we have a diagram over to the right here. There's our sphere or our rod right there. We can see there's our center point here. We come all the way out to the outer surface. That's our outer radius right there, r sub o. Now you can see we have our dimensionless radius right here, which is our r star right there, which is equal to our r over our r naught. So this is similar to our x star that we saw on a plane wall before as we're going out there. So again, this is dimensionless right there. And now we can see we have a temperature of interest at some distance r at some time is equal to 0, and that's going to be our initial temperature there. Then we have our surrounding conditions out here, our T sub infinity, our temperature of the surrounding area right there, and our H value for the surrounding as well. So this again is for convection as we're looking at this right here. So our Biot number is equal to, now we have this relationship here of H times our R naught right there, which again our R naught is at the outer surface right there, divided by our thermal conductivity K. And our Fourier's number here is our alpha T over our R naught again, squared right there. So that's how we get our Biot number and our Fourier number right there, which again are both dimensionless as well. And now you can see we have our dimensionless position right here, our R star. Now, if we want to go back and get those similar one-term approximations like we saw with the plane wall, we can take a look and look at these up separately. Are we dealing with a long rod, or are we dealing with a sphere? If we're looking at a long rod, we can take a look at our equations 5.52 and 5.54 in our textbook, whereas if we're dealing with a sphere, we're looking at equations 5.53 and 5.55 back in our textbook. And again, we can find our coefficients right here and our eigenvalue by looking this up in table 5.1 that we referenced earlier. And now if we want these graphical representations right there, again, if we want to take a look at these figures right now, again, separately for a long rod and a sphere. For the long rod, this is figures right here in our textbook of figure 5S4 and 5S6. And for the sphere, it's 5S7 and 5S9 for those graphical representations where we can get those approximations as well. So next I want to take a look at our semi-infinite solid right here. So what is a semi-infinite solid? It's a solid that is initially of uniform temperature T sub I and is assumed to extend to infinity from a surface at which the thermal conditions are altered. So let's take a look at a couple special cases within this here. So case number one, this is going to be a change in surface temperature right there at T sub S. So we have this relationship right here that our temperature at position equal to 0 and at some time T right here is equal to this surface temperature right here, our T sub S. Now this is not going to be equal to our temperature at X right there, any X, where our time is equal to 0. So that's the difference right there. Temperature right here where we're at a position of 0 and at some time is not going to be equal to the temperature at some position where time is equal to 0 right there. So the inverse, those two are not equal to each other, but this is going to be equal to our initial temperature right there. So now let's reference over to our diagram here on the right, and what we can see is the surface temperature, our T sub S. As we said here, this is going to be our T sub S is equal to our temperature at a position of X is equal to 0 at some time right there. So we can see this is right here where X is equal to 0. If X is starting here and going off like this, this surface right here is where X is equal to 0, and this is why this is our TS right there for our surface temperature. And we can also see that our T sub I here, our initial temperature, could be at any X distance along this direction right here when time is equal to 0. So a way to visualize this down here is if we see on our x-axis here, we have our position in the x direction similar to what we saw up here like that, and we have over here our temperature on our y-axis right here, and we can see as our time changes right here going up like this on these curves right there, we can see okay, at this position we can come up to whatever time curve we're at right here, and we say okay, this is our temperature over here, where this is at the bottom here is our initial temperature, and up here is our surface temperature right there. Taking a look at our equation 5.60 in our textbook right here, we can see we have this relationship here where the difference in temperatures from our temperature at some position in some time right here of interest, potentially what we're solving for right here, minus our surface temperature right there, all divided by our initial temperature minus that surface temperature right there. So that ratio right there, which is our temperature difference, is equal to our ERF here, which is our Gaussian air function right here, times now our position in the x direction. So again, going out in the position in the x direction right there. So that x right there is going to be the same as our x over here, for our temperature there, all divided by 2 times the square root of alpha t right there. So this references back now to this equation 5.60 for our semi-infinite solid right there. Now we also have this relationship here. We can look at our heat flux at the surface right there from equation 5.61. So our heat flux right there, sub S right there, is equal to our thermal conductivity times our temperature difference of our surface temperature minus our initial temperature right there, all over the square root of pi alpha t. So let's take a look at a couple more special cases here for our semi-infinite solid right here. So now let's take a look at case 2, where we have a constant heat flux right there. So you can see our surface heat flux right there is equal to our Q naught double prime right there for our heat flux. We can see that right there is right at this surface here. Our x is equal to 0 at that surface there. So for this case here, for constant heat flux, we have our general governing equation shown here as equation 5.62 in our textbook right here, where our temperature at some position in time right here minus our initial temperature right there, where again our initial temperature is T of x comma 0. So temperature at any position x at some time is equal to 0 is our initial temperature right there, minus our initial temperature is equal to 2 times our heat flux right there, times our alpha times T all over pi to the 1/2, all divided our thermal conductivity K times the exponent right here of negative x squared over our 4 alpha T, minus now our heat flux right there times our x position right there divided by the thermal conductivity times that air function there, times now our x, again that position right there again, divided by 2 times the square root of alpha t. So rather long involved equation, but a lot of these may be things that we either got from a lookup table or are given in our problem statement that we know numeric values for, and we can plug this in and reduce it down and simplify it. But again, for special case 2 right here for constant heat flux, this relates back to our equation 5.62. So now let's move on and take a look at our third case here for surface convection, again, for our semi-infinite solid right here. So if we take a look at this, we're dealing with our H and our T sub infinity here. We have this relationship here now that our negative thermal conductivity K times our partial of temperature with respect to position, where our X is at 0 right there, right at that surface right there, is equal to our H value times the temperature difference right here of our surrounding, or T sub infinity, minus our temperature at that X equals 0 at some time T. So with that, now we can come down here and take a look at our governing equation, which is 5.63 in our textbook right there, where we have our temperature difference ratio right here. We have the temperature at some position and some time minus our initial temperature all over our surrounding temperature minus our initial temperature is equal to this complementary air function right here times our position at X, whatever that X is, divided by 2 times the square root of alpha T, minus now the exponent here of our ratio here of Hx over K, plus now our H squared alpha T all over our K squared right there. And this is now times our complementary air function times now our position X divided by 2 times the square root of alpha T plus our H times the square root of alpha T all over K right there. So again, this references back for surface convection dealing with a semi-infinite solid, and it goes to our equation 5.63 in our textbook. So next thing I want to talk about is this topic of multidimensional effects right here. So as we start talking about topics like this, it makes it more and more realistic and less assumptions and less simplified cases right here. So now if we're talking about solutions for this multidimensional transient conduction, these can often be expressed as a product now of related one-dimensional solutions for a plane wall and an infinite cylinder. So we've looked at both those separately. So this will be multidimensional because we'll be dealing with both the plane wall, which is our P of X comma T, and our cylinder, which is C of R comma T here for the variables that we're going to be using, and or a semi-infinite solid right here, which is S right here of X comma T right there. So each of these is X comma T or R comma T right there. So it's a position and a time right there that these are dependent upon. So we can relate this back to equations on our textbook here of 5s1 and 5s3, along with that same figure we looked at similar before, our figure 5s11 now in this case when we're looking at that figure. So now let's consider the superposition of solutions for two-dimensional conduction in a short cylinder right there. So now we're dealing with 2D rather than 1D situation right here, which would make it multidimensional now. So if we look at right here, the two dimensions we're looking at, this is going to be R and T for those two dimensions right there. Where R is the radius on the short cylinder right here coming out right there. You can see our R outer, our R sub 0 right there. O is right there at the outer surface like that. And now we can see our X position if we start right here at the center right there at our midplane. So you can see this whole circle right here is our midplane. As we go up from that midplane right there, that is our distance X. So this is why it's multidimensional. We have our radius coming out from the center, and we have our X coming up from our midplane. So now if we're coming off that midplane right there, we can see that this right here is equal on either end right this. Definition of a midplane right there, so that's our L, and our L going to the top surface and the bottom surface right there for the short cylinder. And we can come over here and we can see again, we come out from the center right there line out to the edge right there. That is our outer radius, our R naught right there. And any distance coming out from that center along the way until we get that R naught is going to be our radius value R right there. And then we can zoom in on our midplane and take a look at this relationship we see right there. And again, this is that same midplane we see there, same midplane we're seeing right here, like this right here, looking at it in just a simple 2D case right there. You can see as we're coming up from that, we're going up in an X direction there to some position part way up there is X. We go all the way to the surface right there. We can see that as a distance L right there as we get to the outer surface in both directions there. Now, taking a look at this relationship here, we can see now we're talking about our theta terms over our theta sub I. So our theta with respect to R, X, and T over our theta I right here can also be written as our theta of R comma T over our theta I times our theta of X comma T all over theta R. So we can theta I. So we can look at these in terms of radius and position right there off the midplane separately and multiply those together. So this is how we're doing that multi-dimension right there, like we said before. We can express it as both, again, is for a plane wall and for an infinite cylinder separately. So that's exactly what we're doing here. The X is for what we'd see right here, what looks like a plane wall, and our R right here is what we'd see that looks like a cylinder right there. So we're simply saying we can take the cylinder one and we can take the plane wall one and we can multiply them together to get that relationship there. And we recall again that our theta star term right there is going to be our dimensionless one. So we have now our C, which we came up here and said this is how we're defining our C right there, of R comma T right there. Again, R star, T star right there, T star right there. So our dimensionless radius or dimensionless time there is equal to P, which again we said right here, this is for our plane wall, was P right there, of our X star and our T star right there, which is our dimensionless position and our dimensionless time right there as well. So now this comes down now to this relationship we see down below here in this equation, where we now have our temperature with respect to that radius, position from our midplane, and time, minus our surrounding temperature right there, our T sub infinity, all divided by our initial temperature, our T sub I, minus our T sub infinity right there, is equal to now this P of xt right there for the plane wall, times our C of RT right here for an infinite cylinder right there as well. And this is then equal to now for the plane wall and for infinite cylinder, we do these separately like this. So if we look at just this for the plane wall right here, P of x comma t, this is our temperature of x comma t at some position x, some time t, minus the surrounding temperature, all over our T sub infinity minus our T sub I minus our T sub infinity right here, evaluated for our plane wall, times now we do the same thing for our infinite cylinder over here, where this is our temperature of our radius versus, and time right there, minus our surrounding temperature all over our initial temperature, minus our surrounding temperature there again for our infinite cylinder. So that's just saying exactly what we said before, by multiplying those two together for our plane wall and for our cylinder. So now let's take a look at objects with constant surface temperatures or surface heat fluxes. So a transient response of a variety of objects to step change in surface temperature or heat flux can be unified by defining the dimensionless conduction rate. So what we want to take a look at is this dimensionless conduction rate here. So we can reference back to equation 5.67 in our textbook right here, where we have this relationship right here for our Q is our heat rate right there. Now we can see our asterisk right there, our star right there. So that's why we're noting dimensionless. So there's a dimensionless conduction heat rate right there. So this is equal to, on our numerator right here, we have our heat flux for the surface times our L sub C, where L sub C is the characteristic length that depends on the geometry of the object. So for different geometries, that'll change. And this is all divided by our denominator here, where K, our thermal conductivity, times our temperature difference between our surface temperature and our initial temperature. Again, this relates back to our equation 5.67 in our textbook. So now we want to consider a variation of this value for Q here, our dimensionless conduction heat rate, with time, or our Fourier, which is our dimensionless time, for, let's take a look now at interior heat transfer. So this is heat transfer inside of objects such as plane walls, cylinders, or spheres again. So those are the three simple geometry cases right there. Or external heat transfer right here. We're dealing with heat transfer to an infinite medium surrounding an embedded object. So now if we take a look here and see when our dimensionless heat rate here is plotted versus our dimensionless time, or our Fourier's number, we can see that the following is true right here. All objects have the same semi-infinite solid for short times. Our Q star right here approaches a steady state for exterior objects, and it does not reach steady state for interior objects, but decreases continually with our dimensionless time, or our Fourier's number. So we can see our similar behavior between these two graphs right here for our constant surface temperature and our constant heat rate right here. So we can see on the x-axis down on the bottom, we have our Fourier number right here, our dimensionless time unit on both of these right here. And then we have our Q star right there for our dimensionless heat rate on our y-axis for both of these as well. So now if we're looking at our exterior objects right here, we can see there's our exterior objects right here with our relationship for our L sub C. So exterior objects with a relationship for L sub C right there. We can see this is the line right there. If we follow this along here, this is going to reach steady state right there for that guy. Now, when we're talking about this first point right here for short times, how they all behave the same as our semi-infinite solid, we look at our semi-infinite solid right here, and this is the straight line right there. So for short time, so basically up to this time right here of 0.01, these guys all pretty much behave the same right there in that short time duration. Once we get past that point, you can see they start to change right there. There's our exterior right there. There's our semi-infinite right there. Then we come down here for our plane wall, our infinite cylinder, and our sphere right there. Then we talk about the last one here. This does not reach steady state. So as we saw here, it does reach steady state right here. If we're talking about the exterior objects, kind of curves off until it gets to steady state there. But for our interior objects, it decreases continually right there. So you can see all of these are going to decrease continually going down there. So we're talking about some approximate solutions for these objects with our constant surface temperature, constant heat rate right here. We can use our table 5.2. So this right here gives us some easy to use approximate solutions for this Q star times our Fourier number right there. So our dimensionless heat rate times our dimensionless time right there. These are presented in that table right there for all the cases from these figures below right here. So rather than looking at these just from the figures right here, we can now go to that table 5.2. So now let's go to our table 5.2. So part A right here shows a summary of the transient heat transfer results for constant surface temperature cases. So we can see here we have an infinite cylinder right here. So if we're considering that as our example as an infinite cylinder initially at a temperature, initial temperature T sub I, that has a constant heat flux imposed at its surface right here, we can take a look at this table here and we can see, okay, for our infinite cylinder, our length scale, our L sub C here, which again is dependent upon geometry. So for our cylinder, this is going to be our R 0 right there. And our exact solution is now given by this expression shown here. But we also have approximate solutions. We have an approximate solution where our Fourier number is less than 0.2, which is given by this result here, and an approximate solution where our Fourier number is greater than or equal to our 0.2 right there. And we can find its surface temperature now as a function of time. Now we note the difference if we go to table 5.2b. This is now for constant heat flux cases rather than constant surface temperature cases right here. So we can go to the same thing down here. We look for our infinite cylinder. We can see, okay, here's our length, our L sub C is still going to be that R naught right there. Now we have this exact solution. We're dealing with a constant surface heat flux right there. We have this exact solution right here. And we can see we do have still approximate solutions for our Fourier number less than 0.2 and our Fourier number greater than or equal to 0.2, represented by these respective right there and there. So we can see from that table right there that our length scale, L sub C, is equal to that R naught for our cylinder radius right there. And our exact solution for our dimensionless heat rate times our dimensionless time, our Fourier's number right there, is a complicated infinite series right there. So that's something that we want to consider is how complicated that is there. But we do have an approximate solution that we can use as well. So if we take a look down here for our approximate solution, we can see that this right here is a little bit more simplistic right there. So we have this right here for our Fourier number less than 0.2 and for our Fourier number greater than 0.2, which we also got from that table as well. Then it is a simple matter to find our TS from the definition right here so we can back our TS out of this relationship. So now let's apply some of that theory and governing equations to an example problem. So let's take a look at example problem 5.80 here from our textbook, where in this problem they ask us to consider the packed bed operating conditions of a problem 5.12, which I've included below here, but now do it for Pyrex rather than for aluminum right here. So now we have a different density, specific heat, and thermal conductivity other than what was given down here in our problem for aluminum. So we'll use these new values instead. And now they're asking us to use that new information for Pyrex and then find out how long it takes for a sphere near the inlet of the system to accumulate 90% of the maximum possible thermal energy, and also asks us to find the corresponding temperature at the center of the sphere. So we can go back down to this problem 5.12 and make sure that we have everything. We have our diameter given over here. We have our temperatures for our surrounding gas right there. We have our initial temperature here. These are the values that are going to change. We're no longer using these values for aluminum. We're now using the values up top for Pyrex right there in order to solve for those two things they asked us to solve for within this problem statement right here for 5.80. For today's lecture, we're going to continue on with Chapter 5. We're going to be going over the transient conduction, spatial effects, and the role of analytical solutions. We reference back to our textbook. This is sections 5.4 and 5.8. What I plan to do today is to go through a couple of example problems related to this lecture, go through my hand solutions. First problem I'd like to go through is problem 5.80, and in this problem it references back to the same problem we did in last lecture, 5.12. So what we want to do is consider a packed bed operating conditions of this problem 5.12, and if we recall, this is problem 5.12 here, where we had thermal energy storage systems commonly involved in packed bed of solid spheres, through which a hot gas flows if the system is being charged, or a cold gas if it is being discharged, In a charging process, heat transfer from one hot gas increases thermal energy stored within the colder spheres. During discharge, the stored energy decreases as heat is transferred from the warmer spheres to the cooler gas, and they give us this diagram here. So we're going to utilize the information given in this problem 5.12 to go back to problem 5.18. So now that we've looked back at 5.12 to get the information from that problem, we can continue on with problem 5.18. But then again, in this case, we're going to use Pyrex, density of 2,225 kilograms per meter cubed. Specific heat given to us is 835 joules per kilogram times Kelvin, and K is equal to 1.4 watts per meter Kelvin. This is going to be used instead of aluminum. We want to determine how long it takes a sphere near the inlet of the system to accumulate 90% of the maximum possible thermal energy. We also want to know what is the corresponding temperature at the center of the sphere. So we can now zoom in a little bit and take a look at this diagram that was given to us in this problem. It's again the same diagram from example problem 5.12. So here we have our packed bed over here, shown in the center of the diagram here. We have some gas on the outside here, T sub G comma I, and our H value. And then over here for the sphere we have density, specific heat, or K, and our T sub I values, and some diameter of the sphere. So this is all of our given information. From here we'll go ahead and start drawing this out in the right format, same format that we use for our homework and exam problems. Now that we've gone through the given diagram and problem statement, we can now write out all the information gathered from that in the same format that we've seen in our homework and exam problems. For each of these, what we want to do is have 4 different parts to this. We want to know the variable, the value, the units, and then we want to actually have what the name is that relates it back in practical terms to the problem statement. So for all of these, this is going to be very useful as we're going through our key equations to know what to plug in where. And we really do want to pay attention to all of our units. If something needs to be converted from Celsius to Kelvin, we want to do that up here in the problem statement. Make sure everything double checks for our unit analysis and do any conversions in this section here so we can straightforward plug and chug into our given equation. So what do we have given here? We have our diameter, variable name D, value of 0.075 meters for units. We have our density, rho, is equal to 2,225 kilograms per meters cubed. We have our specific heat, C, value of 835 joules per kilogram times Kelvin. We have our K value, our thermal conductivity, of 1.4 watts per meters times Kelvin. We have the temperature of the gas initially. So we can see our units right here for our indices down here. Temperature of the gas initially, Tg comma I, is equal to 300 degrees Celsius. I'm going to leave this in terms of Celsius for now. We have our convection heat transfer coefficient H with a value of 75 watts per meter squared Kelvin. And we have our initial temperature of the sphere, which we've noted as T sub I, which is 25 degrees Celsius. And again, I'm going to leave this in terms of Celsius. Now that we have all the given information presented to us clearly with the right units and the right variable names, the next thing we want to do is figure out what they're asking us to solve for in the problem. So in part A, they're asking for the time required for a sphere to acquire 90% of the maximum possible thermal energy. Part B, they want us to find the corresponding center and surface temperatures. So what we want to do is look back through, now that we know what we're looking for and what they give us, and go through the assumptions we want to make to simplify down the solution to this problem. So we have 3 main assumptions that we want to make here. The first one, we're going to assume 1D radial conduction in sphere. Second part, negligible heat transfer to and from a sphere by radiation or conduction due to contact with the adjoining spheres. And the third assumption is that it's going to be constant properties. So this gives us our first page with all of our given information, what we're looking for, and all the assumptions that we're going to make. So the first step in our solution, what we're going to want to do is to determine if lumped capacitance can be used. So in order to do this, we can reference back to equation 5.10 on page 284 of the textbook, where a Biot number is equal to HLC over K is less than 0.1, where for L sub C we have R naught over 3 for a sphere. And this references back to page 285 in the top paragraph where we can find this information for our L sub C. So we replace our LC with this relationship here of R naught over 3 for our sphere, and this equation 5.10 now reduces to BI is equal to H times R naught over 3 divided by our K value. So now I've left this in terms of variables, but what we're going to do now is plug in our known values for this specific problem. So as we do that there, we see our H value is given to us as 75 watts per meter squared times Kelvin. We have our R naught of 0.075 meters divided by this 2 from diameter down there to radius, and then this is divided by 3 from the equation above. And then the bottom part of this, our K value, which is given to us in the problem statement, is 1.4 watts per meters times Kelvin. So now we've plugged everything in there, and what I want to do is some unit analysis. Double check, see what cancels out, make sure things are in the right units at the end. Watts, watts, meters, the squared there, meters down there, K, all our units cancel out. We're left unitless, which is exactly what we should expect. So we come down here, plug and chug, put this into our calculator. BI is equal to 0.669. Now, this is not less than 0.1, which we were looking for from this equation 5.10 up here. So therefore, a lumped capacitance method is inappropriate. So we cannot use the lumped capacitance method here because we did that check from equation 5.10 and it is not less than 0.1. So therefore, let's proceed and use the approximate one-term solution for 1D transient conduction in a sphere to obtain the desired results. So to obtain the required time, the specified charging requirement, Q over Q naught, is equal to 0.9. Must first be used to obtain the dimensionless center temperature shown here. So this references back to equation 5.55 on page 305 of the text. For a sphere, we have this relationship that Q over Q naught is equal to 1 minus 3 times this dimensionless center temperature, which is referenced right there, with this relationship here. So what we want to do now is to rearrange and solve for this dimensionless center temperature right here. So I'm going to go through a derivation separately here, and we can come up with this relationship shown here once we rearrange everything and solve for this dimensionless center temperature. So now we're going to go through the derivation process in order to obtain the dimensionless center temperature on the left-hand side of our equation and solve for that. So how do we rearrange? What do we need to do in order to get this on its own and solve the equation for this? So the first thing I want to do is take this over here, our Q over our Q naught, which we do have a value for eventually, but we're going to leave things in terms of variables, and move it back over to the right-hand side of the equation and rearrange. The next thing I want to do is divide both sides by this bracketed term. And by doing that, we end up with this term over here on the left-hand side once we switch it over here. And we say 3 times what we're looking for our variable here for our dimensionless center temperature. And we can see there's only 2 other variables we need to remove from this. So first thing we're going to do is we see this is on the denominator here. So let's multiply through by the denominator to get this on its own here. So that's what we do. We multiply through by that denominator. Now we have this relationship here. We have only a 3 over here on the left-hand side before we get this on our own, which is what we want to do. And we can rearrange slightly over here, put the denominator back up top over here when we multiply through. And then from there, all we need to do for the last step is divide both sides by 3. So we divide this by 3 over here, 3 over here, and we end up with this relationship shown here at the end of our derivation. So after that last step of the derivation, we can rearrange and simplify it a little bit more and come up with this nice equation shown here that we're going to utilize for the next step in our solution. So now that we've derived a simplified version of this equation and solved it for the dimensionless center temperature, we then realize that we're going to need to find our eigenvalues in order to proceed with our solution here. Now, in order to get these eigenvalues, we first need to calculate BI, where BI is taken from an equation at the bottom of table 5.1 on page 301 of our textbook. And this gives us that H times R naught over K is equal to BI, where we have these given known values from our problem statement, where H is equal to 75 watts per meter squared times Kelvin. R naught is a diameter over 2 of 0.075 meters divided by 2, and K is equal to 1.4 watts per meters times Kelvin. Plug this in, we end up with BI is equal to 2.01. So now what we need to do with this value is go back to this table 5.1 and look up our eigenvalues. So here is table 5.1 on page 301 of our textbook. And now we can see, okay, for our BI numbers over here, we can go down until we see the value that we have here. We'll have to do a little bit of interpolation from that there, but we can get for plane wall, infinite cylinder, and sphere all of our values. So we can then go over here to what we're looking for sphere, and we can get our eigenvalue and our C value for both of these here. Now that we have values for these from our lookup table on page 301 of our textbook, table 5.1, we know we have our eigenvalue of 2.03 for a sphere and our C value of 1.48. So these values from table 5.1 we plug back into our rearrangement that we just have on the top of this sheet here from equation 5.5. We can plug those values back into this equation there. So here's that rearrangement of equation 5.5. Plug in our known values here step by step. Okay, we have our value up here, which from the table 5.1 is 2.03, value cubed. 3 times, there we go again, our 2.03, 2.03, 2.03. And we have our values over here now of 1 minus q over q naught, which we remember from before was 0.9 from the previous portion of this problem. Then we can go through, start doing out some of the math here, get these values here. We end up with this ratio down here, which when we plug in, this ends up being, for our dimensionless center temperature, a value of 0.155. Next step in the solution is to solve for the corresponding time. And in order to do this, we can use equation 5.53c on page 304 of our textbook. So we come up, and here's our equation here from 5.53c, where we now have several of these values already solved for from table 5.1 and from equation 5.5. I'm going to leave everything in terms of variables, because we now see we have a new variable over here where we need to look at equation 5.36 on page 299 to get the relationship here that f sub 0 is equal to alpha t over our r naught squared. So then we can plug this relationship here back in for f naught up here, and we end up with this derivation from equation 5.53c. So now that we see this here, now we have a value for t in there that we can solve for. So in order to do this, a couple of little steps here for rearranging and simplifying down this equation. We're going to divide both sides by our C1. So we divide this side and this side by C1. We end up with this relationship here. We take a look at this, and now we realize we need to get this t by itself. And the only way to do that now is to do a natural log. So we take the natural log of both sides of this, take the natural log of this ratio over here, the natural log of this over here, and then we end up with this equation here. So now we still need to get t by itself, so the next step in the solution is divide both sides through by our eigenvalue squared term here. And you can see here we divide through this, so now it's 1 over that value times the natural log of this ratio here is equal to alpha t over r naught squared. So the next step in the solution is to go a little bit further with a simplification to try to get t by itself again. So that's what we do on the second page of this solution here. We now see we start up at the top of the equation we had before, and what we want to do now is to multiply both sides by our r naught squared. So what that'll do now is move that over back to the other side on the left here, so we multiply by r naught squared, so it'll just leave us with an alpha t on this side here. So we're almost to where we want to be in solving this for time. So the next final step of this here, we divide both sides by our alpha term in order to get this rearrangement here, where time is now equal to r naught squared divided by alpha times our eigenvalue squared times the natural log of this ratio over here, which we now have known values for. So again, I solved this through in terms of variables, so you can see step by step how we did the rearrangement, but we did have numeric values for some of these variables that we could have plugged in before. I chose not to, so now what I want to do is go through and plug in all these values here. So if I want alpha, I can go to page 78, and this is thermal diffusivity, and this is in units of meters squared per second, where alpha is equal to K over rho C, density and specific heat here. So we can plug in our known values. These are all knowns we have in the problem statement. So alpha is equal to our K value of 1.4 watts per meters times Kelvin. I'm going to do unit analysis just to make sure. Density is given to us as 2,225 kilograms per meter cubed, and we have our specific heat of 835 joules per kilograms times Kelvin. So from this here, we can plug all these values in, solve, and get a numeric value for alpha, which is 7.54 times 10 to the negative 7th. If we do our unit analysis out, it comes out to meters squared per second, which is correct. Plug that back into this rearrangement of the equation up here for our alpha term, and then down here we can then plug this in as a numeric value there and end up with this relationship here for time so far. So now that we have this simplified arrangement now solving for time, we've plugged in for our alpha terms, we see we have an R naught, and we have this ratio over here, which we have values for these that we can plug in. So our R value, again, is equal to diameter over 2, which is equal to 0.075 meters divided by 2, or numerically 0.0375 meters. Our eigenvalue from table 5.1 when we looked it up was 2.03. We solved for this in the very beginning of the problem here, a value of 0.155. And again, from the lookup table on 5.1, we have our C1 of 1.48. So we can take all of these numeric values now and plug them into this equation up above in order to solve for time. So that's exactly what we do here. We start plugging these all in. Okay, our R naught right there, plug this in for this. There's our alpha term. There's our eigenvalue. Plug in our eigenvalue right there. Plug this in here. There's our theta naught term right there, 0.155. There's our C1 term of 1.48. We plug in, and we now have this arrangement here, which we can solve directly for time and get a value of time right here. So 1,020 seconds. Now that was the first part of the problem it asked us to solve for was time. The second part of the problem was asked us to solve for the corresponding temperature. So in order to solve for this temperature, we can utilize equation 5.44 from page 300 of our textbook. We see this relationship here with the difference between the temperatures and the ratio. So with this one here, we can slightly rearrange this for our specific, plug in our values here for these variable names, and then go back through and solve for T naught. So this is what we're going to be solving for. So once we rearrange this relationship here from equation 5.44 with the variable names in it for our specific problem, we end up with the equation that we see up here on the top of the paper here. T naught is equal to T sub G comma I plus we now have this value for theta that we solve for times Ti minus T sub Gi. So we can start plugging in all of our known values. We have this was given to us as 300 degrees Celsius. We already solved for this as 0.155. This was given us as 25 degrees Celsius, and this was given at 300 degrees Celsius. So it's a straightforward plug and chug problem, and I can leave everything in terms of Celsius. Just realize that our final answer here for T naught is going to be given in terms of Celsius as well. We could then take this one step further and solve for the temperature at the surface of the sphere as well. So in order to find the surface temperature, we can go to equation 5.33b on page 304 of our textbook, with our R star is equal to 1. We have this relationship here for this equation here, where we now have our R star that we can plug in for a value of 1 to simplify and reduce this down. We do that, we end up with this relationship here, where we now can use equation 5.44 from page 300, which we just used in the previous portion of the solution, by this ratio of the temperatures here, in order to plug in what we end up with for an equation now, once we've plugged equation 5.44 into equation 5.33b, we can see this relationship that we see here. And within this, we can now solve for our T sub s, or our surface temperature, based on this relationship here. So that we rearrange this, solve for a Ts, and what we end up with for an equation is this here. T sub s is equal to T sub g comma I plus T sub I minus T sub g comma I times this over here on the right, where all of this is now known numeric values that we can straightforward plug and chug. So everything has a value associated with it. So T sub s is equal to 300 degrees Celsius plus 25 degrees Celsius minus 300 degrees Celsius. Then we plug in here for our theta term 0.155 times the sine or our eigenvalue divided by our eigenvalue there. And what we end up with when we plug this in is that our surface temperature is equal to 280.9 degrees Celsius.